Okay, in this next video, we're now going to, now that we've talked about the sinusoidal source, we're going to talk about the sinusoidal response. And you're going to have to bear with me on this video. This particular video is a little technical as far as all the details. It's a little mathy here, but I promise you once we get into the analysis a little bit more, we'll get to not have to be so mathy in our computations and get to an easier analysis technique. So the sinusoidal response, that's what we're going to be looking at. So we're going to first start off with a simple circuit. It's one that we've analyzed in the previous course. And for some reason I drew that really big. I want to redraw that. You know me, I can be a little bit picky about how I want to draw these. And so we're going to have a simple RL circuit. And then we're going to close this at t equals 0. And we're going to have a voltage source here. And then we're going to say is, basically IL 0 plus is equal to 0 amps. There's basically, it's been open for a long time. There's no current, no energy stored in the inductor. Okay, so we're going to take that approach there. And then my Vs in this case, well, we're studying sinusoidal responses. So my sinusoidal we're going to have here is Vm, just like we had in the previous lesson, cosine omega t plus phi. So that's what we're going to be looking at as far as my analysis here. Now, we're going to do a real simple analysis here. We're just going to go ahead and do a KVL. I'll just write a loop here. And just to kind of dust off the cobwebs from the previous course, remember we'd get here kind of starting at the voltage source, you'd get minus Vs plus voltage across the resistor plus voltage across the inductor is equal to 0. Now we're going to go ahead and move Vs to the other side. And so we'll go ahead and substitute everything in here. So of course we know if we label this current here just simply, I don't want to use capital. Usually capital is reserved for DC and we're looking at AC here, so I'm going to look at lowercase I. So of course we have Ohm's law for the resistor, so we have I times R. And then remembering the current voltage relationship for an inductor, we would have the inductance times the derivative of the current going through the inductor. And then this is going to just equal Vs, which is, again, just Vm cosine omega t plus phi. Alright, so now what do we have here? Well, we have a differential equation, and all of you hopefully at this point are either currently taking differential equations or have already taken it. And this is what type of differential equation? If you guys look at this, you should be able to identify that this is a linear first order differential equation. Now, I'm not going to go through all of the theory on how we do this, but some of you should recall, hopefully most of you recall, how do you solve these? We use something called an integration factor. To solve this. Now, before I even get ready to use the integration factor, in order to get this completely set up, what we're going to do is we're going to rewrite this differential equation as I plus L, I'm sorry, I'm doing it the wrong way here. Let me erase this. We're going to write this as dI L dt is plus r over L times I is equal to Vm over L cosine omega t plus phi. Then my integration factor, which is often denoted as rho, depending on your differential equation textbook, it would be different, is this e to the integral of r over L dt, which that's easy to do that integral. This just becomes e to the r over Lt. Now, what we're going to do here is we're going to take this term and we're going to multiply the previous equation by that. Now I'm going to kind of do a dot, dot, dot and skip some steps here because fortunately we're not going to have to go through and solve these differential equations every single time, but we want to at least be able to understand what this sinusoidal response is and be able to understand how it is we're going to analyze these problems in the future here. Okay, so then what we get here is we wind up with the resulting equation. You'd have the derivative of t with derivative with respect to t. If you'd have I times e to the r over L t is equal to e to the r over L t Vm cosine omega t plus phi. And how you get this, again, that's really reserved for a differential equation course. It's really what you're happening here is that if you take this, because you have two things multiplied here, and you apply the product rule, you would wind up with this previous line, of course, having been multiplied by this e to the r over Lt. Now what's nice about here is this derivative is outside of this bracket. So if I integrate both sides, I'm just going to slap an integral on both sides. Well, then the left-hand side just becomes I e to the r over L t is equal to the integral of e to the r over L t Vm cosine omega t plus phi. And, whoops, this t looks like it's in the wrong spot there. That should be up in the exponent, t. And what's nice about this is I is what I'm trying to solve here. I'm trying to find the current. And so once I do this integral on the right-hand side, I should put dt here, I would just simply divide by this term here, and I'd have what I is. Now, the frustrating thing about this integral is that it's not a trivial integral to do. It's not a difficult integral to do, but it is a little messy. You have to do integration by parts. If you remember back to Calc 2, I'm sure you did an example of this in Calc 2, but I will let you do that on your own if you would like to see that. So I'm going to put in a couple dot dot dots here. So we're integrating and then we divide by it. And so the end result we get here is I is equal to negative Vm divided by the square root of r squared plus omega squared L squared cosine of phi minus theta e to the minus r divided by L t plus Vm over the square root of r squared plus omega squared L squared cosine omega t plus phi minus theta. And so this would, of course, the units here would be amps. Now, this is the final result. Now, this theta is just an additional phase angle you get because what ends up happening is you get both, when you do this integration here, you get both cosine and sine when you do the integration by parts. And so when you have that, you can actually change when you are adding and subtracting cosines. There's a way to convert that into just a single cosine function using, again, some trig identities. And so that's where this cosine of phi minus theta comes from. So we won't have a specific formula for theta here. We'll see when we get to the analysis that that kind of just falls out naturally for us. But there's two kind of important things I want to point out here. This first portion here, we call this portion here the transient response. Now, why would we call this the transient response? Well, let's look here a second. What do we have here? Well, we've got this negative Vm, all of these terms here, and I'll go ahead and maybe put this in gray here, or green. I'm going to put a little box around these, a light little box. Everything in here, none of those are variables. Those are all just numbers. Vm's a number, the resistance is a number, omega squared is our angular frequency, and L squared is the inductance. Those are all numbers. So this is just a number sitting out. Well, this here, that's also just another number. There's no t involved with that. That's cosine of phi minus theta. And again, I don't necessarily know what those are, but that's just a number. So this whole thing right here is just a number. And then I have my exponent, which has got my t. Now I've got r over L, and actually, if you wanted to rewrite this just like we taught about in the previous course, this is actually t divided by tau. I'm just writing it as minus r over L times t, but it's t divided by tau. But notice again here we have this negative. So what do we know as t goes to infinity? What is going to happen to this exponential? Well, we should all remember that what happens to that exponential is that it goes to 0. So this whole term goes to 0 as t goes to infinity. Now, that's why we call it the transient response. At t equals 0, there's stuff going on here. But remember, how many time constants do we say before these transients go away? We said 5 time constants in the previous course, and again, depending on who you talk to, it's either 4 or 5 time constants. I like to use the rule of 5 time constants, but some people like to use the rule of 4. But then now let's look at the other term that we have sitting in this response here. This we call the steady state response. And let's examine why we call this steady state. So, well, again, what we have sitting out in front of here, this is just a number. Same reason, that's just what's sitting over here even. And then we have cosine omega t plus phi minus theta. Now these are just phase shifts on the graph of a cosine function. So wait, I have a number times a cosine function. We know that a cosine function, does that forever, right? Just goes up and down forever. So we have some transient response that goes on, but then eventually that transient response goes away, and the final output of the current is that I have a sinusoidal cosine function that just goes up and down forever. So this is what we call the steady state response, and that's what, of course, we're interested in at the beginning of this course here. That's the first main topic we're going to do, is how do we find the steady state response. Now, if we look in this video here, the way you would find the steady state response is not necessarily a fun way to do it. The way we would do it here is you have a circuit, you write your differential equation down, and now this is a linear first order differential equation. You solve your linear first order differential equation, which we skipped tons of steps in solving it, and you get your answer. And we get both my transient and then my steady state. What we're wanting to see is there's got to be a better way to be able to get from here. We're hoping that there's a better way to get from here to the only portion I'm concerned about in steady state analysis is this portion right here. In steady state analysis, we're only concerned about the steady state response. We're not interested in the transient response. So we just want to figure out a way to get to that. And it turns out we have some clues to us already in front here. We have this r squared here and then an omega squared L squared going on there. And it turns out we're going to be able to make a lot of progress, and it turns out the analysis is going to be very similar to a lot of the analysis we did in the previous course. So we're going to end this video here. The next thing we're going to talk about is what tools we are actually going to use to do that analysis, and then we'll be able to start doing some analysis.